Welcome back to the OpenUK Mini-Moo lessons. This is lesson 9 and it's called Light Glove. You can start and stop this video at each step if you need more time to keep up with the lesson. Kavita was looking through the input palette inside the MakeCode editor and found lots of other exciting input blocks. She found one that says Light Level. This gave her the idea of building a two-handed glove project that uses light level to vary the tone as she moves her hand up and down. She's not quite sure how to make this work though. Can you help her with the code? In today's lesson, you will help Kavita write a program for her glove called the Light Glove. By doing this, you will use many things you've already learned about in MakeCode, including event handlers, variables, including Boolean variables, if statements, functions, passing parameters to functions. You will also learn how to return a result from a function, how to map a range of numbers to a new range, how to round a number to the nearest digit, and of course, you will learn a little bit more about open source software. You will need your assembled Mini-Moo glove and the MakeCode web coding editor. You might also need a pair of scissors or a needle and thread. When Kavita mentioned that MakeCode could sense the light level, I didn't quite believe her. I got my microbit out and looked all over both sides of the board and I couldn't see a light sensor on there anywhere. It's a mystery. So I went over to the pages at microbit.org and found some information about it. It's really magic how this works. The LEDs on the front of the microbit will light up when told to do so by your program. However, an LED, which stands for Light Emitting Diode, is quite magical because it can also be used to give a rough estimate of how much light is shining on it. This is how the light level block on the microbit senses light. To do that, the LEDs need to be visible and, oh dear, some of your microbits may be hidden away inside a little pocket on the glove. It's either time to get the scissors out again and cut a small hole in the pocket, or you could remove the microbit and sew it onto the front of the pocket. Let's get started on the code for this light-sensing musical glove. I'll zoom in to this first bit of code up on the left here. There are some important numbers we need to set up first. I think we'll set these as constants so we can reuse this program for other things another day. Vmin will be the smallest value that is expected from the light sensor, and Vmax will be the biggest value from the light sensor. The microbit website told me that the light sensor produces a number between 0 and 255. 255 is a strange number for the maximum. I must read up about that later on the website. Tmin will be the smallest tone frequency the glove will sound, and Tmax will be the biggest tone frequency. I went over to the music palette and used the keyboard there to click on different piano keys to work out a good range for these numbers. Set step 1 for now, and I'll explain that later. Also set a Boolean variable to true and add in the onLogoUp and onLogoDown event handlers. This will all start to make sense when we look at the other parts of the program. Let's move over to the right here a bit and look at one of the functions we need to write. This function is called sense, and it's responsible for sensing the amount of light shining on the microbit LED screen and turning that number into a useful range of musical tones. So, this is where all those constants become useful. We have to take the light sensor reading, which is between 0 and 255, and convert it to a tone frequency, which we want to be between 262 and 784. The maths for that could be quite tricky. Fortunately, there's a block for that. It's called map, because it maps a range of input values to a new range of output values automatically. That doesn't sound very clear, does it? Hey there, Mr. Illustrator. Can you help us out again, please? I think we need a diagram to help us understand what this map does. Perhaps you can draw it as I explain it? Let's imagine on the left-hand side we have this bag of numbers of different values. Let's say 5, 7, 9, 3 and 2. Let's sort them into order and decide that they are always between 0 and 10. Yes, that's it. Over on the right-hand side, let's have a second bag of numbers. Let's say 4, 18, 6, 14 and 10. And let's sort those into order too. We can decide that these will fit within the range 0 to 20. To map from the left-hand bag of numbers to the right-hand bag of numbers, we draw lines between each matching pair. So, 2 maps to 4, 3 maps to 6, 5 maps to 10, and so on. Can you see what map does for these numbers? Yes, in this case, it multiplies by 2 to get from the number in the left bag to the number in the right bag. If the numbers in the bags had different ranges to our earlier example, then the map would do a different mapping for us. Thanks, Mr. Illustrator. That's great. Fortunately, the engineers at Microsoft have done all the hard maths for us, so we can put any numbers into the map block and it will work it out. This is super handy because it means with one block and a few constants, we can map the range of numbers from any sensor to any range of numbers that will generate a tone. The last part to look at here is what the return block does. We can just think of this a bit like the opposite of a parameter. When a parameter is passed into a function, we said it is like posting an envelope through the letterbox with something inside it. The return is just like putting something else in the envelope, scrubbing out your address and posting the envelope back out to the return address, written on the back of the envelope, return to sender. In computing, we say that the function returns a value to the caller. There's one more bit of code I want to explain. I'll let you read the help pages later about the round block. Let's use my joystick here and move the screen around a bit. I want to get both the sound function and the forever loop on the screen together. Right a bit, yes, that's it. Let's look at the final puzzle pieces here. The sound function has a nested if inside it. We've used those before. It also has an absolute block inside it. We've used those before too. Actually, all the blocks in this function we've used before. But this code pattern looks a bit new. Can you see what it does? This bit of code clearly solves some problem, but I wonder what. Well, I have 2 microbits here that are programmed slightly differently. The first one just has a ringtone block in it with the if playing block. Let me turn that one on and let's listen to the sound together. Oh dear, that's a terrible noise, isn't it? It's all crackly and glitchy. Now, let me turn on the second microbit and let's listen to that. Here goes. Oh, that's better, isn't it? It doesn't keep clicking all the time and is a bit more pleasant to listen to. Let's look back at the code and see why this extra bit of code makes it sound better. As it turns out, if you use the ringtone block repeatedly when the pitch hasn't actually changed, the microbit will stop the speaker sounding for a fraction of a second. Then it will turn the speaker back on again with the same pitch. If you don't change the pitch, what you hear is the same pitch stopping and starting very quickly, and that makes that horrible clicking sound. The absolute of block, here, is used with the pitch parameter, and another variable we called old pitch. Now, old pitch is just the pitch of the sound we played last time this function was called. So, this code is looking at the difference between the old pitch and the pitch. If the pitch has changed, it will start the new pitch ringing, and then remember this new value in the old pitch variable. This is another common programming pattern that you will see all over the place in large programs, and it's basically detecting when something has changed. Oh, Kavita has just reminded me that I promised to explain what the step constant is for. It just sets a threshold for how much the number in the pitch variable has to change before it's considered a different pitch. If we set this to 10, for example, then the pitches of our musical glove will be much more steppy. If you've ever heard singers use a feature called auto-tune to keep their voices in tune, it's just like that. Don't forget to put in the forever loop, as that joins together the sensing and the sound parts, and it won't work if you miss that bit out. Right, get your code flashed onto your microbit. Then, stand under a light or stand outside. Move your other hand up and down and side to side across the LED display of the microbit and see what sounds you can create. You might need to fine-tune your light glove a bit to get it to work really well, and we would usually call this process of fine-tuning calibration. Do some experiments with it, and you can make the V-min higher and the V-max lower to change the range of light readings that it responds to. Make sure that V-max is always a lot bigger than V-min though, otherwise you might get some very strange results. V stands for value, and it's the value read from the light sensor. To change the range of tones or pitches that get generated, you can change the T-min and T-max constants. These numbers are actually the frequencies in hertz of the pitch. You can get these by clicking on the piano keyboard in the Play Note block, or you can look them up on the internet. If you want a slightly stepped effect, a bit more like auto-tune, try changing the step constant to something like 10 and see if that effect is more or less pleasing to the ear. The ultimate test, though, would be to try and play along with a simple tune with your light glove. Kavita is looking up Andy's YouTube channel now to see if she can play along with any of the tunes there. She's also planning to team up with Amanda and Matthew later. She thinks that the light glove, the jingle glove, and the harmony glove might work well together as a small orchestra. That's super work, team. What a great project. Let's finish off and look at how open source software can be shared. There are many websites on the internet that allow you to publish your code and share it for others to read, modify and use. All you need to do is put the code somewhere, like GitHub, and make sure you have added the copyright notice and a license. Without a license, it just wouldn't be open source. By publishing code in this way, you allow and actively encourage people to use it and modify it. So, we're going to try a little experiment. Amanda has some friends that run the school e-zine, and they've recently added a coding corner to the e-zine. Let's send an email with our code to them and see if we can get it published for others to try it out. Where's my email program gone? Ah, there it is. From the Coding Club to School e-zine editors. Subject: Open Source Code. Dear editors, we would like to submit a microbit program for inclusion into the coding corner of your magazine. The code plays different tones as you move your hand up and down, blah blah blah. The Coding Club. Attach hex file. Send. Great. So, hopefully the e-zine editors will like our new program and publish it in the weekly school e-zine. We may even get some feedback from the readers about our program. Ooh, I'm excited already. I wonder if they will publish it. There are lots of ways you can share and publish your programs, but remember to add the copyright notice and the license so people know you created it and what you are allowing them to do with your program. We'll check back next week to see what the editors of the magazine thought about our program.